Colligative properties. Colligative properties are properties of solutions. Recall that a solution is a homogeneous mixture of two or more pure substances. The components of a solution are the solute, which are the dissolved particles, and the solvent, which are the particles which are doing the dissolving. Solvent-solute interactions are very important in solutions. In fact, the solute can often affect properties of solutions depending upon its nature and its concentration, and generally these stem from the interactions that the solute particles have with the solvent. In a true solution, the solvent particles and the solute particles are approximately the same size. Because of this, in terms of colligative properties, the identity of the particle is not particularly important because most of the particles will be approximately the same size as each other. Thus, it's the quantity that is important and not the quantity. The properties like this, which are dependent upon quantity and not identity, are referred to as colligative properties. Now, colligative properties are properties that are concentration dependent, not identity dependent. There are four basic colligative properties which exist in solutions: vapor pressure lowering, boiling point elevation, freezing point depression, and osmosis or osmotic pressure. Generally, we express colligative properties in one of two concentrations. Molality is a unit which expresses the number of moles of solute per kilogram of solvent. This expresses concentration in absolute units, which are not dependent upon the physical state. Recall that molality, then, is one of the only units which actually looks at solvent rather than solution in terms of the denominator here. Molarity, the other M property that we look at, is a measure of moles of solute per liter of solution, and in this case, since it's measuring volume, volume is a physical property which depends upon the state the substance is in. Molality measures only the moles, which is a measure of quantity, and kilograms, which is a measure of mass, neither of which are variable. Mole fraction is another unit which is often used in colligative properties, where this represents the fraction of the number of moles of one particle versus the number of moles of all of the particles in the solution overall. We can look at the effect of colligative properties, and we find that the overall effect that we get from colligative properties is less than what we would expect on a mole per mole ratio for things like ionic substances or substances which ionize. The reason for this is that some ions in solution will interact with each other, and when doing so, they behave as a single particle. This causes the overall number of particles that the solution thinks are in the solution to decrease, which decreases the overall effect of the colligative properties. Lowering vapor pressure is the first colligative property we will talk about. Lowering vapor pressure occurs in substances which have non-volatile solutes. These can either be solids or liquids as solutes. Lowering vapor pressure depends upon Raoult's law. Raoult's law states that the addition of solute to a solution will decrease the liquid vapor pressure of the solvent in that solution proportionally to the concentration of the solute which is added as a mole fraction. Solute occupies space in the solution, and in doing so, it will block the surface of the solution, which prevents solvent molecules from being able to rise to the surface and vaporize. Because the process of evaporation increases entropy, and the reason that it does this is as particles move from a liquid phase to a gas phase, they become more disordered. The idea of evaporating a solution is going to increase the overall entropy of the solution. A pure solvent will increase overall entropy as well, just like a solution will. Now, a pure solvent is much more ordered in its liquid phase than a solution is. As it transitions to a gas, the gas is more disordered than the liquid. For a solution is already disordered versus a solvent because it's a mixture of more than one thing. Because a solution is already disordered, there is less disorder to be gained in a solution by evaporation, which means that the overall benefit of the entropy gain in a solution versus a pure solvent is less. As with all colligative properties, the only thing that matters are the number of solute particles in the solution. Raoult's law applies only to non-volatile solutes. Any sort of volatile solute can actually raise the vapor pressure in an additive form, as we'll talk about later. Lowering vapor pressure follows Raoult's law, in which the liquid vapor pressure of the solvent over the solution is what is being measured. We can express this mathematically, where P solvent, which is the vapor pressure of the solvent over the solution, is equal to the mole fraction of the solvent particles times the pressure of the vapor over the solvent as a pure solvent. So we have P solvent, or P solution, interchangeably, which is the pressure of the solvent over the solution, X is the mole fraction of the solvent, and P not solvent as the pressure of the vapor over the pure solvent. As an example, if we're given a solution of 0.2907 moles of glucose and 16.65 moles of water, what is the vapor pressure decrease of this overall? If the vapor pressure of pure water at 25 degrees Celsius is 23.8, how much does this decrease from 23.8? We can calculate the mole fraction of the solvent with 16.65 moles of water in relation to the total number of moles of particles in the solution as a whole, which is the 0.2907 moles of glucose plus the 16.65 moles of water. This gives us a mole fraction of 98 or 0.9828. We can then plug this into our equation, finding that the pressure of the solvent is equal to 0.9828 times the initial vapor pressure of 23.8 torr. This gives us a pressure of the vapor over the solvent in the solution as 23.4 torr, which is a slight decrease from the 23.8 torr of the pure solvent. Any solution that obeys Raoult's law is referred to as an ideal solution. We can determine the difference in vapor pressure using Raoult's law if we consider that the amount of the vapor pressure lowers is the change in vapor pressure delta P. So the pressure of solvent is going to be equal to the mole fraction of solvent times the pressure of the solvent in pure solvent. We look at the change then in the pressure of the vapor over the solvent as being equal to the pressure of the vapor over the pure solvent minus the pressure of the vapor over the solution. As a fraction, the mole fraction of the solvent plus the mole fraction of the solute should equal 1, since adding together fractions overall should come to 1. We can rearrange this then to solve for the mole fraction of the solute as 1 minus the mole fraction of the solvent. If the change in pressure of the solvent is going to be equal to the initial pressure of the solvent as a pure solvent minus the pressure of the solvent in solution, we know that the pressure of solvent in solution from the first equation is the mole fraction of the solvent times the pressure of the solvent of the pure solvent. We can factor out the pressure of the vapor over the pure solvent, leaving us with the change in vapor pressure being equal to 1 minus the mole fraction of the solvent times the pressure of the vapor over the pure solvent. This 1 minus the mole fraction of the solvent is the same as the equation above, where we have X solute equal to 1 minus the mole fraction of the solvent. So we can substitute this in and find that the change in vapor pressure of the solvent is equal to the mole fraction of the solute times the vapor pressure of the vapor over the pure solvent. This allows us to demonstrate how much a specific concentration of a solute will lower the vapor pressure from that vapor pressure of a pure solvent. Non-ideal solutions are those which do not obey Raoult's law. Not all solutions will. These solutions tend to follow different trends from solutions which are ideal, and oftentimes will raise the liquid vapor pressure in combination. Any solution that consists of 2 or more volatile liquids combined will actually combine their liquid vapor pressures in solution. This causes them to boil at a lower temperature, and both of the liquids will be carried over. The liquid that has the highest liquid vapor pressure will be the highest concentration in this mixture. So as we continually distill the solution with the liquid with the highest liquid vapor pressure will continue to increase its concentration versus the other liquid. Eventually we can separate out this liquid which has the highest liquid vapor pressure from the solution with the lower, or the liquid with the lower vapor pressure. We can accomplish this by continual distillation through simple distillation, or we can accomplish this by what's called fractional distillation. Fractional distillation relies upon a column that has a series of packed things inside of it. This is referred to as a fractionated column. What's packed inside of the column can be things like copper wire or glass beads, anything that has a high surface area. The liquid which has the lower liquid vapor pressure, therefore the stronger attractive forces, will attract more to this surface area than the liquid with a higher liquid vapor pressure. So the lower liquid vapor pressure liquid will stick more to the surface than the higher liquid vapor pressure liquid will. As they move up the column cools, and the solution with the lower liquid vapor pressure will condense faster than the one with the higher liquid vapor pressure. This causes the higher liquid vapor pressure liquid to move further and further away from the one with lower liquid vapor pressure. Eventually, the one with the lower liquid vapor pressure will recondense and form a liquid again. The one with the higher liquid vapor pressure can escape and be collected as a separate liquid. The longer the column is, or the more packed the column is, the larger this effect will be, and the greater the separation that can occur through fractional distillation. Boiling point elevation is the second colligative property we talk about. It relates to the lowering of the liquid vapor pressure because we know that liquid vapor pressure is the pressure of the vapor over the liquid, and boiling point is the temperature needed to raise that liquid vapor pressure to reach atmospheric pressure. If the liquid vapor pressure has decreased from what it normally is, this requires even more energy to get it to equal the atmospheric pressure and reach the boiling point. So the boiling point will increase if the liquid vapor pressure decreases. This causes the boiling temperature to increase, and we can measure this mathematically as the change in the boiling point being equal to a constant times the molal concentration of any solute in the solution. The constant is referred to as a proportionality constant that is called the molal boiling point elevation constant. This measures the change in the boiling point, which occurs by a 1 molal ideal solution and is measured in degrees Celsius per molal. The m represents the molality of the solute, and the delta Tb is the increase in the boiling point that occurs. As an example, what mass of ethylene glycol in grams must be added to a 1 kilogram sample of water to produce a solution that boils at 105 degrees Celsius? The Kb of ethylene glycol is 0.512 degrees Celsius per molal. So we have our equation. We can solve for the molality as the change in the boiling point divided by the Kb constant if we rearrange the equation. Plugging this in then, the change in the boiling point goes from 100 degrees Celsius to 105 degrees Celsius, or a 5-degree change. So we divide 5 degrees Celsius by the constant 0.512 degrees Celsius per molal, and this gives us a solution that is 9.77 molal. We take our 1 kilogram of water, multiply it by 9.77 moles per kilogram of water as the molal concentration expressed in moles per kilogram, and this gives us 9.77 moles of ethylene glycol. To find the mass that is needed then, we can take our 9.77 moles of ethylene glycol, multiply it by the molar mass of ethylene glycol at 62.07 grams per mole, and we wind up with a total of 610 grams needed to create a molal solution that accomplishes this boiling point elevation.